MS Ramaiah University of Applied Sciences.
Hello students, let us have a discussion on uncertainty analysis in experiments. Aim of the experiment is to determine the uncertainty of a result in an experiment and to plot the graph of the result showing the uncertainty using error bars. In this exercise, suggest on suitable changes to reduce errors in the experiment will also be made. Let us consider a scenario where a thermometer is being used to measure body temperature, where the reading on the thermometer shows 37 degrees Celsius. However, the accuracy of measurement of temperature is not noticeable with just this result. The reading would show 37 degrees Celsius even if the actual temperature is 36.9 or 37.1 degrees Celsius. Hence, in order to understand the surety of a measurement in an experiment, we calculate uncertainty in the result. There are numerous sources of errors involved in an experiment or measurement that leads to uncertainty in the result. Different sources of errors include the measuring instrument itself may suffer from errors. The item being measured may not be stable. When measuring the size of an ice cube in a warm room, due to the two-phase nature of ice and water, it is difficult to measure. The measurement process itself may be difficult to make. Some measurements depend on the skill and judgment of the operator. For example, the use of an instrument such as a stopwatch depends on the reaction time of the operator. Environmental conditions like temperature, air pressure, humidity, and many other conditions can affect the measuring instrument or the item being measured. By taking into consideration all the errors in the measurement, an uncertainty value gives a good measure of the quality of the result. Uncertainty in measurement or result is denoted using plus or minus symbol. For example, measurement of body temperature by a thermometer yields a result of 37 plus or minus 0.1 degree Celsius. Hence, 37 degrees Celsius is the nominal value and plus or minus 0.1 degree Celsius is the uncertainty in the measurement of temperature. Hence, due to some errors, the actual temperature may lie anywhere between 36.9 to 37.1 degrees Celsius. Hence, the temperature to lie in the specified range is ensured. Higher the range indicates higher uncertainties in the measurement. If R is the result of an experiment and x1, x2 up to xn are the different independent variables responsible for the result, then we can write the result R as a function of independent variables x1, x2 up to xn. Uncertainty in the result R can be calculated as shown. In some cases, the uncertainties associated with independent variables are not available, and also partial derivation may be complex. In such cases, a small increment delta xi may be taken as a representative of the uncertainty. The least count of an instrument can be an example for the small increment. Procedure to calculate the uncertainty of a result can be followed through 4 steps. The first step is to calculate the nominal value of the result. Second step is to identify the independent variables that are responsible for the calculation of the result. Also, the uncertainty of each variable is to be noted down. If uncertainty of variable is unavailable, take least count of the varying parameter as the uncertainty. Third step is to calculate the partial derivative of the final result with respect to each variable. Finally, the uncertainty in the final result using the formula is calculated. Let us solve an example and calculate the uncertainty. The resistance of an RTD sensor are at a temperature T degrees Celsius having copper wire material is given as R equal to R naught into 1 plus T minus 20, where R naught equal to 6 ohms plus or minus 3%, alpha equal to 0.004 ohms per ohms degree Celsius plus or minus 1%, and T equal to 30 plus or minus 1 degree Celsius. The nominal value of the resistance is calculated by just plugging in the nominal values of R naught, alpha and T in the resistance equation. We get a nominal value of 6.24 ohms. In the next step, the independent variables are identified and their uncertainties given in percentage are converted to absolute values of uncertainties. Uncertainty in R naught is given as 3%, which is multiplied by 6 ohms to get an uncertainty value of plus or minus 0.18 ohms. Similarly, when 1% of 0.004 give us an uncertainty of plus or minus 4 into 10 to the power minus 5 per degree Celsius. In the third step, values of partial derivatives of R with respect to R naught, alpha and T are calculated. In this manner, partial derivative of R with respect to R naught yields a value of 1.04. The partial derivatives of R with respect to alpha and T give values of 60 and 0.024 respectively. In the final step, the uncertainty with respect to R is calculated using the uncertainty formula. Uncertainty value is found to be plus or minus 0.19 ohms. Final result with uncertainty may be expressed as R equal to 6.24 plus or minus 0.19 ohms. When we divide 0.19 by the nominal value 6.24, it gives uncertainty of plus or minus 3%, which can also be represented as R equal to 6.24 plus or minus 3%. The solved example is repeated for varying temperatures and a graph of nominal wire resistance against variation in temperature is plotted. We can also observe red lines marked at each data point. These red lines on the data points are called error bars, indicating the uncertainty in calculation of resistance of the wire. Now that we have calculated the uncertainty, let us look into its use in reducing the errors. The final equation in calculating the uncertainty contains terms that is equal to the number of independent variables. The product of the squares of partial derivative and its individual uncertainty for every variable is to be compared. The partial derivatives and the square of the product of uncertainties with the partial derivatives for the solved example is tabulated here. We can observe that with the value of 0.035, the square of the product is highest for R naught. In spite of high partial derivative value with respect to alpha, the square of its product with uncertainty yielded very low value. The parameter having the highest value of the product will be responsible for the maximum error in the result. Uncertainty can be reduced by replacing the gauge parameter having the highest product with the better equipment. In the solved example, since 0.035 is very large when compared to 5.76 into 10 to the power minus 6 and 5.76 into 10 to the power minus 4, measurement of R can be made with the better equipment. That is, a measuring instrument having an uncertainty value of less than 3% is to be used in the measurement of R naught.
At MSR UAS, we spark your imagination unlike any other.